High-speed typing often produces physical keystroke errors that software must intercept and map back to the intended target strings. This is measured through the Levenshtein Edit Distance, a metric defined by 3 operations: inserting a character, deleting one, or substituting one for another. The final score rests in the bottom right cell. Tracing back to the origin reveals the exact edits. Dynamic programming avoids redundant calculations by breaking the comparison into overlapping subproblems, storing each result to build the optimal path efficiently. The Wagner-Fisher algorithm has a clear computational cost. It requires both O of m times n time and space to execute. Allocating that quadratic space takes negligible system memory when you are autocorrecting a 10-character search query. The computational limit emerges when applying this algorithm to massive sequence alignments, such as comparing 2 100,000-line codebases or sequencing biological DNA. If we zoom out to map 2 10,000-character sequences, the system attempts to allocate 100 million individual cells into memory. At this scale, the algorithm fails physically. It exhausts the computer's available random access memory and crashes the process. To bypass this limitation, engineers shifted the paradigm, viewing string comparison through graph theory. This diagram translates the matrix into Meyer's edit graph. Intersections become nodes, connected by directed arrows. Moving horizontally represents a deletion, vertically an insertion. Diagonal edges carry 0 cost, forming the shared skeleton, the longest common subsequence, between the strings. Under this model, sequence alignment is a shortest path problem. The task is to route the most efficient traversal from the source to the sink within a directed acyclic graph. Because the cost of any cell depends only on its immediate neighbors, we do not actually need to store the entire history of the matrix. This enables the 2-row trick. The algorithm only needs to hold the current row and the row immediately preceding it in memory. This optimization collapses the memory footprint from a 2-dimensional matrix into a highly efficient single-dimensional array. For legacy systems, storing a full quadratic matrix was often physically impossible. Row discarding was a technical necessity to process data on early hardware. This reduces space complexity down to O-mn, providing a way around the memory wall. However, this spatial optimization introduces a critical engineering trade-off. While the 1D array successfully calculates the final edit distance score, it has discarded the historical map required to reconstruct the path. Tools like git-diff cannot function on a score alone. They require an explicit edit script detailing what was added or removed to modify a file. We solved the memory bottlenecks at the score, but made it impossible to retrieve the actual sequence of edits. The solution is a linear space divide-and-conquer strategy developed by Dan Hirschberg and later adapted for edit graphs by Eugene Myers. The algorithm abandons the single, continuous forward pass through the graph. Instead, it uses a bidirectional approach. The memory-efficient search runs forward from the start and backward from the end simultaneously. Both of these frontiers maintain the O of n space limitation by holding only their leading edges in memory. By attacking the graph from both ends, the algorithm can identify an optimal intersection point without retaining the full graph history. When the forward and backward searches collide on a common diagonal, they identify a middle snake. This meeting point is proven to exist on the optimal shortest path. This point fractures the search space into 2 smaller, isolated bounding boxes. The algorithm recurses, repeating the bidirectional search inside these new boxes to find their middle snakes and split them further. This pins down guaranteed waypoints, allowing the software to reconstruct the route without ever holding the full map in memory. By storing only the split points and discarding the matrix rows, the space overhead forms a converging geometric series. Compute time remains O of mn, but space complexity is reduced to O of m plus n, linear space. This optimization enables version control systems to parse millions of lines of code and generate accurate diffs using only a fraction of a computer's memory. This mathematical efficiency is what makes modern version control and large-scale genomic sequencing possible on standard hardware today.